Hi everybody, welcome to Mrs. John's lesson. Today's lesson is lesson 2 for DC electricity for year 13 physics. It is mainly a revision of year 12 physics, but I'm also introducing a little bit of new concepts in this lesson. Now today's lesson is largely about how we calculate total or effective resistance. But before that, just look at some of the other quantities we deal with in electricity, what we're familiar with, the word voltage and current, and then I'm going to move on to resistance. Now, you know, voltage is the amount of energy carried by charge, and the voltage across a battery or a source of power is the property of the source, and it doesn't change no matter how many components there are in that circuit. So if this is a 9-volt battery, and let's say the voltage across this lamp is 4 volts, then the voltage across the resistor is 5 volts. Now the voltage across the components, that is the lamp and the resistor, all depends on how many components there are and how they're connected. So here's another example. So there's a series circuit, here's a parallel circuit. So if this is a 9-volt battery, you know that the voltage across each branch is the same. So just to elaborate what is a branch, the best way of identifying how many branches there are in a circuit is actually to look for junctions. So what is a junction? When you're driving along a road, you come to a junction and you usually have traffic lights, and the reason why you have those is that is where there's more than one pathway. You have an option of either going straight or turning to the left or turning to the right. You also have what are called T-junctions, you know, where you have two of them meeting. So when you look at this is not a junction. These corners is just a bend in it. It's just turning direction. So these are your junctions. And a junction actually tells you how many branches there are. So you've got this branch on the top, you've got the middle branch, and you've got the bottom branch. Now in a parallel circuit, the voltage across each branch is the same. So that's 9 volts here, so this will be 9 volts, and I can just divide this into 6 volts and 3 volts, so they add up to 9. I've got a slightly different circuit over here, talking about voltages. If this is 9 volts and this one is already taking up 4 volts, the remaining 5 volts goes up there. Okay, this is something we did in year 12. So that's about voltage. Okay, so the voltage of the source remains the same, but the voltage across the components all depends on how they're connected and how many of them there are. The next thing we're looking at is current. Now, current drawn from the battery, okay, that is the term we use, current drawn from the battery. It all depends on how many components there are, and not just how many, how they're connected. And the size of the current all depends on the total voltage and the total resistance. So this is where we come to the resistance. Now the total resistance actually depends on how the resistors are connected. And you have learned in year 11 that for a series circuit, your total resistance is, you just add them up. And for a parallel circuit, the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3 and so on. Okay, so in a parallel circuit, the more resistors you add in parallel, the total resistance decreases, and the total resistance in a parallel circuit is always less than the least of the resistor's value. Now, what does resistance mean? So I have a demonstration to explain the meaning of resistance. So I'm just going to turn my camera, and you think, oh my goodness, what is this? So I have here a nail board. And why do I have a nail board? And I also have some marbles over here. Now let's say you can magnify the inside of a wire. So you have a connecting wire through which charges move when you have a current, when they're connected to the end of terminals of a battery. So the nail board is depicting the inside of a wire. So why do we have the nails? Now the nails represent the nuclei of the atoms that make up the wire. So this could be copper atoms or aluminium atoms, whatever the metal is. The marbles here are actually the valence electrons. So metals have very few valence electrons that can easily leave the atom. So these are the valence electrons that are free to move. Now, if the metal wire is not connected to anything, these electrons just move at random, not in any particular direction. But when the ends of a wire are connected to the terminals of a battery, there is an electric field, and so the electrons experience an electric force and they all drift to one end of it. And when they do so to show that there is a potential difference, they're going to move from a region of high potential to low potential. And to show this high potential, I'm just going to lift this end. And when that happens, you can see all the marbles moving down to the other end. And it makes this lovely noise because these marbles are actually colliding with the nuclei of atoms, and they're actually losing some of their energy. So they slow down. If these nails were not there, they would roll down really fast, or if there were fewer nails, they would roll down faster. And as opposed to that, if there were more nails and they were really closely packed together, they would slow down even more. So the slowing down of electrons, or the slowing down of charge as it moves through a wire, is what's called resistance. Okay, and resistance is measured in ohms, and it tells you how difficult it is for the charges to move, or bigger the resistance, smaller the current. Now in your workbooks you've got some questions on calculating effective resistance using these formulae, but there's also one other thing that I want to bring your attention to, and that is, if you have a circuit that is not closed, but there is a gap in the circuit, you know that no current will flow through that circuit because there is a gap. So let me just draw that circuit for you and explain that concept. Let's see. Okay, you can see the circuit over here. Let's say this is a 12-volt battery. So you know how the long line is the positive end and the little line is the negative end? So when I say it's 12 volt, we say that the positive terminal of the battery is at 12 volts and the negative terminal of the battery is 0 volts. So there's a difference in potential of 12 volts. Now the voltage across this branch will be 12 volts and you can have a current flowing. But there's a gap here. There is no current flowing. However, this end is at 12 volts, at this end is at 0 volts. So there's actually a potential difference. If I can call this A and B, there's a potential difference between A and B of 12 minus 0, 12 volts. So this is what I want to bring to your attention, that even though there's no current flowing, you could have a potential difference between a gap. That's why you have sparks flying across gaps. Okay, bye for now, and that's the lesson.